Okay, so hello everyone. Um, Usually I cannot join the meetings due to scheduling conflicts, but today I'm here to present this chapter for the efficient optimization. Okay, let's see. So the first thing, the chapter starts with a quote that says that the real problem is that programmers have spent far too much time worrying about efficiency in the wrong places and at the wrong times. Premature optimization is the root of all evil in programming. With this quote, what the author is trying to tell us is that trying to optimize a code that is yet not finished or is in a premature part of the process can lead to being inefficient instead of speeding things up. So in this chapter, we will go through several functions, several, I will say, like tricks to know about R, about the base R, about every function or most functions, in order to efficiently change change our code in order to, well, get a faster code. Here are the prerequisites, the packages that we will need. ProfBees is to get the code profiler, is to get where some bottlenecks are. The RCPP package is to run C++ functions on R. So the 5 tips for getting better performance on our R code. First one is use a code profiler to know what you need to optimize. If you don't know, if you only try to guess where do you need to optimize your code, well, it can lead to some problems. It can lead to you optimizing what you don't need, ignoring what you need to optimize. So it is very important to know where the bottleneck is. The second tip is that if all data on a data frame is the same type, considering converting it into a matrix, a data frame is like a generalization of a matrix where you can has a lot of types. After that, well, we have the table. I don't know if we pronounce it like that. It is like a generalization of a data frame. But if we have any of those two with all data of the same type, we can convert it into a matrix, and that will speed up everything. Use a specialized row and column functions. This is because R is a vectorized language. So specialized row and column functions are already vectorized, so they will run faster. We can use the parallel package. The parallel, well, at least from what I know, I have never seen anyone use parallel programming. It is something like very ignored, or at least from what I've seen. And the last tip is consider rewriting parts of your code in C++. I know that a lot of functions in R are like compiled in C++. I haven't really do like any programming in C++. I don't know almost anything, only what I wrote, what I read in this chapter. Okay, so let's continue here. So first, for the code profiling, as I was mentioning before, the objective for the code profiling is to determine where the bottleneck of your code is, so you can know what do you need to optimize. We can use base rprof function, or we can use the profbees package. The profbees function is, we write it as this. In this example, Okay, let's see here. This is the example. Oh, yeah, I don't know what happened here. So this is the main example for the monopoly package. For the monopoly function of the EfficientR package, we do the profbis function. Here we have like the memory and the time that it takes to run that function. And we can see that most of the time it's here in the move square function compared to, well, everything else. It takes like, well, I don't remember, but it takes almost all of the time to run that move square function. That is because we are using a data frame and an apply function that both are like iterative, I could say. So they take a lot of time to run. Well, in here I had another example that I wanted to test. I was working, trying to get a Gibbs sampler. I was trying to see where the bottleneck is. And in here, well, what I do is that I take a lot of samples from a gamma function and a lot of samples from a normal distribution. And I can see that here, the gamma and the norm distribution, well, the random values of those two distributions, it's what takes almost all the time on the program that I'm writing. I'm not really sure if I can speed that up, but yes, I was just wondering how will that look on an example of mine. So now we start to compare some functions. The author will give us some tips on some functions that we use almost, well, very often. The first one is if else, and this versus if. The if else is a vectorized way of writing if and else that we use on R. Here we have an example. We have some marks that are samples, random values from an uniform distribution with minimum 30 and maximum 99. We use this if else where if the marks is greater or equal than 40, we say pass, and else we say fail. Using this base R if else function, it will give us an elapsed time of 1.75, I think. I'm not sure if those are microseconds. I'm not really sure. If we do this here with this function, this is a writing one that, well, takes, from my point of view, takes an advantage of the vectorize and the matrix language of R. So if we take that, results in like I'm not really sure how to say it in English, but we see that this part, this writing function, it is a lot faster than this if else, even though the if else it's supposed to be vectorized. And also we have the if else function from dplyr, where first is like more readable, and it is a lot better than this one, the base R function. But still, this one is the one that is faster than both of those. I don't know if there are any questions or comments about this. Okay, so I linked here an example. I was trying to find an example that, well, give us some difference of the if-else function and the base if-else. First thing that we have is that if-else is stricter than, well, the dplyr if-else is stricter than the if-else. The if-else, the dplyr function, expects a Boolean argument from the output of the first parameter. So in the if-else, we need to write something that gives us a Boolean argument, so we can calculate what needs to do after. For the base R if-else, it says that it is not very clear about what does it expect from the first argument. You can put it, you can put like a Boolean argument, 0. It takes some values, and that lack of clarity, I could say, it can lead to some errors, as it was shown in the example. Let me open it here. I don't know if you can see the new page that I opened.
Yes. Yep.
Okay, so in this case, if we have a vector, we need to, if a red flag, if the vector is greater, the sum of the vector is greater than 11, and a green flag is if it's less than 11. So we create an alert object that is if else, if the sum of the vector is greater than 10. In this case, since it takes here, it calculates each value. If it's greater than 10, it gives us zeros and ones and sum those values. It doesn't make a lot of sense, but still, the if else, if we print it, it will give us a red flag. From here, we do not have like a Boolean argument, but still it gives us an answer. So, well, in this case, it says that we need to like be careful to how we use those two values. From another difference that I found is that the if else has a built-in handler for NA values, the dplyr one, and also the dplyr one preserves data types. So they advise to use the dplyr one whenever it is possible. From sorting and ordering, well, the author says that sorting a vector is relatively quick. And if you don't need the full vector being sorted, you can use the partial argument. So in this case, we create a vector of length 100 and we sort it. From here, we use the argument that we only going to sort the first 10 numbers, and we print the first 16 values. So as you can see here, the first 10 are sorted, but from here on, it is random, but it is not sorted. As you can see here, well, minus 124. We have here minus 129, minus 114, from the 10th one, it stops being sorted. So that's how we use the partial argument. The author says that there are 3 sorting algorithms for the sort function. We can use the shell, the quick, and radix. I tested the 3 of them, and yes, it is true that the radix is the faster one. That is not the radix, it is not the, how do I say it? The default one. And I really didn't, I don't know if anyone looked up what is the default one.
Yes, I think in the book they say it is not the default one, but I think now it is documented that it is the default currently.
Oh, okay, so the radix method is the default one.
Yeah, so that explains also why you get such fast results by default. Yeah.
Okay, perfect. So in the sort function, the radix method is the default one. In here, the author says that we can reverse the data by using ref or sort x, and the parameter decreasing equals to true. And this sort, it will be faster than rep. In this case, well, we can see that it is true, not by a lot, but yes, we can see that using the sort and the parameter decreasing to equal to true, it is faster than rep. Some other functions that the author will give us some tips on how to use more efficiently is that to determine which index of a vector of arrays are true, instead of using which and the vector equals to min, we can use which.min, and here it will give us, well, almost 1/3 faster. Other function that the author explains us that we can use more efficiently is this one, to converting factors to numerics on a data frame. And for the logical and on or operators, these are already vectorized functions that returns a Boolean value. They return false or true. The non-vectorized version I didn't know about. Is this one with the 2 symbols, but we need to be careful with that one because, well, it only calculates the second component if needed. For this example of on top, if we use this one, it will only calculate this one. It doesn't matter the result on this one, it wouldn't calculate this one. In this example, it is useful because first it will calculate if it's NA. If we get it true, well, we convert it to false. And if it is false, we don't calculate the other part. If we do not have any value of NA, it will go then and calculate the mean of X. Now for the row and column operations, we can use the apply function. This function does this type of operation like very quick and easy to read. So we have the apply. It is a family of functions that we know: the apply, the apply, the supply. Where we put the data set, one if we want to do the function for the rows, and 2 if we want to do on the columns, and the function name that we need to calculate. Instead of that, if we can, we should use some optimized functions that takes like advantage of the vectorized nature of R, such as row sums, call sums, row means, and call means. More of these functions can be found here on this package, on the matrix.package. I'll link it here. I didn't know about this package, and it has a lot of functions that we can use, like row collapse, row counts, row sums, row interquartile range, means, medians, quantiles, range, invariance, weighted means, and all of that optimize to the vectorized nature of R. So instead of doing an apply, we can use one of those functions on the matrix.package, and it will be a lot more optimized. Now for the isNA and NENA, we can use both if we want to see the NA values of some object. If we want to test if an object contains missing values, we use isNA. But if we need to find if it has any missing values, we should use NENA instead of isNA, since the author says it is more efficient, it is more optimized.
If nothing else, that one's more like typing optimized. I didn't know that existed. I've written any is NA X like many times, and that's one of those that okay, like I'll use that. It's up there with lengths. I don't know if you don't know about that you can take the length of everything in a list with just put an S on length. I had written that a million times before I learned it existed as well. So
yes, I also didn't know about that function. I always use the isNA. So, well, for the matrices now, all matrix, as I was saying before, all matrix elements must have the same type, and matrices are generally faster than data frames. We can use data point matrix to convert data frame into a matrix. I used as matrix. I don't know why it isn't mentioned in here, but it appears to be that data.matrix is the more optimized way to turn something into a matrix, or a data frame at least. Now for the integers, the author says that the numbers in R are usually stored in double precision floating point format. This is a format, it is not an integer, and each double precision number is accurate to around 17 decimal places. So if I have like a number for a double precision floating number, I will need, I didn't write it here, but if I print it with 17 decimal places, it will give like 2.0000, and at the end, another number. That is why it is not an integer. Integers in R are usually written as the number and an L that it is about. It means literal, yes. It means literal, and that's how we know that that number, it is an integer, not a, well, double precision floating point number. In here, we create an object from 1 to 10,000. We see that it takes up to 680 bytes. And these are integers. These will be integers. In here, we do the same one, but we create it as a sequence that it goes this 1.0. I understand that it's saying to R that it will be a floating number, not an integer. And as you can see, it takes a lot more space. So integers usually take a lot less space than double precision floating numbers. Now for the sparse matrices, this is a matrix where most of the elements are 0. If opposite, where most of the elements are not 0, the matrix is considered dense. We can calculate the sparsity of a matrix by the count of zeros, the ratio of the count of zeros with the total elements. The author tells us 2 ways of creating, or not creating, a sparse matrix, but to look at a sparse matrix. The first one is with the sparse matrix function. This function, what it does is, it does not save like all the zeros. Instead of that, it saves the, I don't know how to say it in English, like the direction of the zeros, the location of the zeros. So it saves a lot of memory. And from here, we create a diagonal matrix with 1 on the diagonal and zeros on the other side, and every other, from size 10,000 times 10,000. We can see that the sparse matrix, it takes a little bit of space. It doesn't take a lot since it is optimized. And the object size, the size of this matrix, it is 800 megabytes, which is, well, a lot of space to have stored in R. Sparse matrices are difficult to handle because most of the matrix operations that we need to do have a hard time when they have a lot of zeros. Sparse matrix, we can see them, I don't know, I was reading an example like says that if we have a database of a movie database where a person, the database is 1 if the person has seen a movie and 0 if it hasn't. So in that case, it will have a lot of zeros and it will be an sparse matrix. Now, the author shows us an example of how to optimize the move square function for the the move square function, yes, for the monopoly function. So 3 tips that we have seen until now is that first, instead of using that data frame, we use a matrix. Instead of using apply, we use row sums. And instead of using that logical operator, we use the vectorized one. And that will give us, okay, give me 1 second here. I didn't wrote it. It says that this will give us like a 25 times faster or a 10 times faster, well, between lines. So in total, it will be like the code will run like 20 times faster than the original code without these 3 changes. Now for the parallel computing, this part I was saying that it is like, from what I've seen, well, don't take my word for it, because I haven't seen a lot of R, or a lot of people using R very good. So it is like very ignored. Only one teacher has mentioned it to us. And in this case, what it does is that it uses multiple cores of your computer that lets you run multiple processes in your code at the same time. It comes installed with base R, so we just need to call it library parallel. And it can, the first thing that the author tells us is that we can detect the cores. In this case, well, I will have 12 cores for this computer. The most common application is with the apply family of functions. So instead of writing lapply, apply, or sapply, we use par before that, and that will give us the parallel version of that. CL, it is a clustering. I don't know if I wrote it here. Yes. So CL is basically a parameter of clustering. In this case, for example, as an example of what the author was saying, it takes the snake's ladders example, and we run it a lot of times. And the first thing that we need to do is we need to make clusters with this function. I was reading that the optimal way, or the recommended way, is that we use the number of cores minus 1, so we can still have one core available for any other task that we are doing at the moment. So this number, the number of cores minus 1, it will be our cluster. Now, if we apply that, we can see here, we can see that we apply it instead of sapply, we wrote par sapply. And if we compare both of them, this one is a lot faster than the sapply. It goes from 4.46 to 0. So it takes a lot less time. The author also tells us that in order to avoid, how was it called, memory leakage, we need to run this function, stop cluster, every time we do a cluster. We make cluster in order to stop the memory leakage from R. I was seeing some examples of that, and some people were posting screenshots where on the task manager, it shows a lot of our tasks with a lot of RAM consumed. So yes, we need to be careful with that in order to stop that memory leakage to happen. If now the author explains us that if we do this on a function, we have to be very careful, because if we use this stop cluster inside the function, it can make the function stop, just stop from continue. Instead of that, we use this on .exit stop cluster, and well, that will like fix it to stop. That will like fix it to prevent this function from stopping the whole function. Now, if we want to do this parallel coding under Linux or OS, what we do is that we use these functions, mclapply or mcmapply. Well, in this case, I think we have to write mc before the function. What it does different to Windows is that it creates a new copy of a process running on the CPU. So you don't have to start and stop cluster objects. This is called like forking, if I'm correct. And it doesn't work on Windows. In Windows, if we do this, it will still use one core of our CPU. Now for the RCPP, what it does, this package, is that it offers an integration to use C++ language within R. The author, well, it says some difference between C++ and R language that I have here. The first one, that in the C++ function, each line must be terminated with a colon, I think it is called. In R, we use colon when we have multiple statements on the same line. The second difference is that we must declare object types in the C++ version. And in particular, we need to declare the types of the function arguments, return value, and any intermediate objects we create. I'm not familiar with C++, but I would assume that declaring objects before doing anything, it is a way to optimize everything. The third difference is that the function must have an explicit return statement. Similar to R, there can be multiple returns, but the function will terminate when it hits its first return statement. The fourth difference is that you don't use assignment when creating a function. The fifth one is that object assignment must use equal sign. This one that R uses, like the arrow operator, is not valid. I always use like this equal sign, since like it works for Python and for R, so it is like more generalized than the arrow one. And another difference that the author tells us is that one-line comments can be created using the double dashes, if I'm correct. And the multi-line comments are created using this one. Now, for an example, if we want to write a C++ function on R, we use the function cpp function. This is from the library rcpp. In here, well, it doesn't show the way it is. Let me open R. Oh, but I don't know if you can see my R.
We cannot.
1 second here. Okay, so in this case, this example, this is the example that I was trying to show. Since I don't know why Markdown, it doesn't, since this is like, well, let's say for R, it is like a comment. I'm not really sure about that, but it shows like this. I'm not really sure why, but this will be the correct way to start a C++ function on R. So here we state that this will be a double object, the name of the function, what we expect to get on the function, and the type that we were going to return, the operation that we need, and here we say that it is going to return this double value object. In here, we can see that we already can use it. We can just write the name of the function at CPP, and here it is. At CPP, it will be equal to 3. The most efficient way is to put, now, we need to put your C++ code on a separate file, and that is made using the function source CPP and the code where you want to start the function to compile it. After that, we need to do this part, include the name of the function or the name of the path, or the name of where you store it. And in order for you to stop using like, give me 1 second here. It says here on the book, if we, so we use this include rcpp.h, that will be the function. This include, it's like our library. So after we do that, instead of doing this part, so we call the package and the function. To avoid that, we just use this using namespace rcpp. And from there on, we can just write it as any R function, the name of the function, and the parameters. Okay, this is another example of how to write a C++ function on R. This will be for an iterative function. As you can see, before any variable, we need to specify the type that we need. And here we have the iterative part of the function and the return. So that will return the min. What RCPP adds is that it helps to write C++ function on an R style. So instead of doing this, this will be the way of doing it in C++. We can write it as this. And this will be more like an R way to write that function. As you can see, we can use POW, the POW function. And as we can use that POW function, we can also use another functions like the author says, like all the, for example, rnorm, I think, all those statistics functions, we can use them to write C++ functions. And that will be it for this chapter. I don't know if anyone has any comments on this. I'm not really, as I was saying, I don't really know anything about C++ apart from what I wrote in this chapter.
I have edited C++ for a package before. I've never written it. But it's I mean, it's something I would like to add to my tool belt for sure. Just haven't gotten there.
Because as C++, it is a compile language, it is faster than R. And I know that a lot of packages in R are wrote in C++ under the hood.
The most useful reason to get comfortable with C++ is, or in my mind, is that there's a lot of stuff that's already written in C++, so you can wrap that into an R package once you know how it works. I know what's it, clock is like it's what's under the hood for Lubridate now, and he uses a C++ library that does all the heavy lifting with dealing with time stuff. So that kind of thing is where I would like to start learning some of that. But lots of very interesting stuff in this chapter for sure. I thought it was interesting. So many of the examples when they would show the timing, like the actual time difference is tiny, and that really points out the, don't optimize from, like, don't bother with these kinds of optimizations other than just knowing how to write, knowing to write them. But it's not going to gain you anything if it's something that you call once. If you call it, some of these you have to call it like 100,000 times before you would even notice that there was any difference. And so it definitely drives that home of don't waste human time trying to make the computer very slightly faster.
But in this case, the small difference of time, it wouldn't be because we use like small examples.
No, because a lot of those had like,
Well, it had
like very large
big numbers.
Yeah. So it would, and even if it is a small example, a lot of times, the point being that if you're only calling the thing like once per data set versus like once per row of the data set or something like that, you want to optimize the things that are getting called over and over and over the things that just get called once. So that's what the profiler is for. I am not good at using the profiler, but I know it exists and I want to get better at it.
In that first example that I used, I don't know why it doesn't show like, oh, now it showed this part. It almost never shows. I don't know why. And also here on the slide, I don't know if kind of books out. It doesn't let me select anything else. But yes, that profbis, I think it can be really helpful, but it is kind of weird to use. It is not like very user friendly, or from what I see.
Something else to think about is if you have like code that's working and it's fast enough, it might actually get slower if you try and run it in parallel, because you'll take a performance hit from setting up the cluster and then also chunking out the input into each of the different sections. And so if you don't have enough data, it will be slower than if you just did it linearly.
No, I thought that in general that profiling, that parallel coding, it will always be faster.
It's like running the code itself will be faster, but there's like setup time required that ends up making it slower if there's not enough data.
Oh, okay.
It's sort of like a constant setup time plus variable based on the data. So if your setup time is greater than your total time for linear, then it's going to be slower.
Oh. I don't know if anyone has any more comments.
Actually, I have tried this profviz on Mac OS. It doesn't show any window in RStudio. I don't know. It's if it's a problem due to latest Mac OS Ventura, or have you tried it in RStudio? But I think you are using Windows.
Yes.
Okay. But I have tried it like 1 week ago. This window doesn't show on Mac OS for profviz package.
I don't use Mac, so I can't help, but like most of the developers at our studio do use Mac, so I don't know what's up there.
I can try it, but I think I've used it before, and you get the same kind of visuals, which basically tells you, what kind of code, how much time it takes to run. But I can try another example and I'll share that in Slack later.
Okay, maybe this is due to when Mac OS latest update or something. Okay, I will check. Maybe there is some problem or something other.
Yeah, if you have a sample code that you want to try running on yours and other others to play, I can try and replicate it.
Okay, thank you.
Okay, if there are none any more comments, thanks everyone for the attention. This is my first presentation of on the club. I hope it was good, and I will try to get better.
Well, thank you very much.
Particularly liked that you showed some timing examples, that you really actually executed all the code and showed how quickly it went. That's very cool. Thank you.
Thanks.
Yeah, thank you.
So much.
All right, bye.
Bye, everyone.
Goodbye.